from me and Mr. Pizza. Here's the news.
Okay, today we're looking at a new topic, but it's something we've actually talked about previously. At least you're familiar with the notation, and it's all about functions. And I'll show you what a function is and the sort of questions you might have to be able to answer. So a function can be thought of as like a machine. They have different names, and they're using this sort of notation, f of x or g of x or h of x. Quite often f and g's and h's are hanging around. But it's where you put a number into this machine, and the machine does something to it, and then out pops a different number. Well, sometimes the same number, but usually a different number. So this machine, to get from 4, it goes into the machine and out pops 10. It could be doing something like plus 6, or it could be whatever you put in, you double it and then you add 2. And the function can be defined using a little algebraic formula. So this could be f of x is equal to 2x plus 2. Let's say it's doubling it and then adding 2. So when the 4 goes in, this machine takes that 4 and puts it with the x's. So you have 2 times 4 is 8 plus an extra 2 is 10. And if I was to put a different number into this machine, I would get a different solution. If I put in, let's say I put in 5, I would have 2 times 5 plus an extra 2, which would give me 12. So a function is defined with a little formula, something like this. And these are exactly the sort of things we were differentiating a few weeks back. And here you can have a function that's called f. You could have another one that's called g. This could be, you take whatever you put into the function g, and the number gets squared, and then you subtract that away from 1. So if you had g of 10, you would have 1 take away 10 squared, which would be 1 take away 100, which is minus 99. Or you could have an h. Let's say the h was, I don't know, 30 minus 7x. So if you put in, let's say we put in h of 4, you would have 30 take away 7 times 4. So it'll be 30 take away 28, which is 2. So a function has to be defined in some way, and you put some numbers into it and out come different numbers. And this could be the basis of a graph. It could be a quadratic or a straight line, all sorts of different shapes. But in this sort of section, we have to deal with this function notation and then start working with them. So let's actually look at this notation in more detail. Let's say we have the function f, and f is defined as being 3x minus 1. And we have another function. Let's say we have g of x, and g of x is the function which is 1 minus x squared. And these two are different sort of functions, and if you want to substitute a number in, the notation works like this. You put the number in brackets. So we say that as f of 2, and that means 2 is going into this function. So you have 3 times 2 minus 1, which will give you 6 take away 1, which is 5. If you put a negative number in, it still works in the same sort of style. So you'd have f of minus 3. It'd be 3 times minus 3, take away 1. So I'm just following the same pattern. This is the definition of what f of x is. So whatever number you put in, it has to be 3 multiplied by the number you put in, take away 1. So this will give me minus 9, take away 1, so that's minus 10. If you do happen to have a squared bit in your function, you just have to be very careful if you're substituting in a minus number. So if you had g of minus 7, for example, we have to do 1 take away minus 7 squared. And it helps to use brackets if you're putting a number into your calculator which is negative. If you square it, we know that that can go wrong unless it's in brackets. So that'd be 1 take away minus 7 squared is 49. So it's 1 take away 49, which is minus 48. You can even go one step further and you can start to put in algebra into these functions, which we'll come to in a second. But you could also have problems that involve the function itself. Let's say we had f of x, and we know it comes out to equal, let's say it is 29. And we need to know the value of x that gives you 29 for this function. So you can solve a little miniature equation. 3x minus 1 is what f of x is defined as being. We're looking for the value of x that gives us 29, so we can solve this equation. If you know what f of x is, and you know what it's going to come out to be, then you can just solve this equation. So add 1 to both sides, divide by 3, so I get x is equal to 10. So if I was to put 10 into here, I get 3 times 10, which is 30, take away 1, gives me the 29 I need. Now, function notation is a strange thing. It can be written in lots of different ways. You can have ones that you've seen already. So f of x is equal to, let's say f of x this time is equal to 10x squared plus 4. But sometimes it's written like this. It can be f dash dash, not dash dash, dot dot of x is 10x squared plus 4. And sometimes it's even written like this, is with an arrow of 10x squared plus 4. These are 3 different ways of writing exactly the same thing, and they mean that you take the number, you square it, you multiply it by 10, then you add 4. But sometimes questions in textbooks can look in any one of these forms, but they basically mean the same thing. Just historically, people have written functions in different ways. So if I define a function like this, it doesn't matter. I would still take f of x is equal to 10x squared plus 4 is my basic way of thinking about it. And if I wanted to do f of 2, I would do 10 times 2 squared plus 4. Using BIDMAS, I would do the things in brackets first. Do the indices next, so that's 2 squared is 4. So I've got 10 times 4 plus 4, which gives me 44. So the function can be written like this, or like this, or like this, but it means the same thing. Sometimes, if you have a function, you can be asked to substitute in not just a number, but something more than a number, maybe some sort of expression. So let's say we had f of x is defined as being, let's say this is going to be 10 minus 4x. Okay, so this is the function no matter what. So if I put a number in, that's easy, that's what we've been doing. Well, that x is a bit shiny there, that should dry in a sec. But you can actually substitute in anything. So I could substitute in, for example, smiley face. And that would give me 10 minus 4 times smiley face. Or I could be asked to substitute in some sort of algebraic expression. So I could put in like f of y plus 1. Whatever happens with this function defined like this, whatever goes in this bracket appears here where this x is. So if I'm substituting in y plus 1, the function tells me it's 10, take away 4, times that entire lump. You can simplify that if you like, but you don't need to necessarily. So even if I had something involving x's, say if I had, I don't know, 3x plus 2 over 5, if I was substituting this expression into my function f, which I've defined up here, I would have 10 take away 4 times all of that horrible lump, 3x plus 2, all divided by 5. And again, I could then simplify that. And you can take this even one step further. And if you have 2 different functions, let's say I've got f of x is equal to 3x plus 1, and I've got g of x is equal to 1 minus x squared. Of course, I can put numbers into them, I can put algebraic expressions into them, but you can actually start to put entire functions into another function. So I could have f of 1 minus x squared. Now that expression there is my definition of what g of x is. So this is really taking g of x and substituting it into f of x. If I did that, I would have 3 times whatever I'm putting into there, 3 times all of that, plus an extra 1. So this is actually equivalent of g of x being put into f of x. And often that is just written as fg of x. And you sort of read it, if you see it written like this, you read it from right to left. This is taking g of x and substituting that entire expression, 1 minus x squared, into the function f. So it goes here. And if you were to do it the other way around, if you had g of f of x, that's meant to be an f, that would be taking the entire function f and putting it into this function. So that would be 1 take away all of that squared. So this is a g of x is 1 minus something squared. the something I'm putting in there is f of x, and f of x is 3x plus 1. So I've got 1 minus 3x plus 1 squared. So you get a whole range of like nested functions within functions. Let's do another one like that. Let's say we start with, let's have a k of x, 2x plus 3, and let's say we have an e of x, that could be just x squared, and we could have an n of x. I could go further and spell out the word Kennedy, but that would take ages. N of x could be, let's say it's 1 divided by x plus 4. And you can have a whole combination of these three different things. You could have ke of x. Ke of x is taking the function e of x, this one, and substituting it into here. So that would be 2 times x squared plus 3. It's the e of x here going into this function k, and you read it from right to left. You do the e first, you grab it, and you put it into the function k. So the e of x goes here. You get 2x squared, that's meant to be an x, plus 3. If I had k of n of x, that would be taking the n function, grabbing it and putting it in here. So it would be 2 times 1 over x plus 4 plus 3. So both of these are quite similar. You're taking something and you're putting it into k, and again you're reading from right to left. It would be the other way around if I wanted to find out what, let's say, n of k of x. That would be taking the expression k of x and putting it into this function n. It would be something much more complicated. So I'm taking my k of x, this whole thing here, and putting it where the x is. So I get 1 over 2x plus 3 plus an extra 4. So it looks a lot like the n of x. It's taking the k of x first and then putting it into the function n. So I get something that looks like n, but instead of x, I've got the thing I was putting into it, which was the k of x. And whenever you see something written like that, you have to read it from right to left. The last thing we have to be able to do in this chapter, or in this subject, it's not a whole chapter, is involving inverses. Okay. If you want to write an inverse of a function, it looks funny. So if the original function is written, let's say this is 2x plus 7, the inverse is written like this: f to the power of minus 1 of x, or f of minus 1 of x. This is the inverse, and it does the opposite of whatever this is. If you put 10 into here, you get 27. So the inverse would be, if you put 27 in, you'd get back 10. So if I have f of 10, I get 27. The inverse function does it backwards. I put in 27 and I get back 10. In order to do that, I have to work through this formula backwards. For this one, if it's 2x plus 7, what I would need to do, this one multiplies by 2 first and then add 7. The inverse function would subtract away 7 and then divide by 2. It's the opposite of what I do to get that 27. If I put 10 in here, I do 2 times 10 plus 7. Here, if I wanted to find out what to do backwards with the 27, I'd have to take away the 7 first and then divide by 2. And there's a way of finding the inverse. This one's relatively simple because you just think it through and then work backwards on the steps. What we do is you write it more in a traditional style. Let's say the way we might have written this as a straight line equation is y equals 2x plus 7. That takes the x coordinates and puts them onto the y-axis. So you have a coordinate where all the different x coordinates are multiplied by 2, then you add 7. The inverse function does the opposite. And to find the inverse function, you can swap the x and y axis over and then rearrange it to make y the subject. Here, if I subtract away 7, I get 2y, and then I divide by 2 to finish off with. And this is the longest way, this is the sort of the logical way of finding the inverse if it's not obvious. Let's do another one like this. Let's say I have a function f of x is equal to 3x squared minus 8. Okay, so if I want to find the inverse function, I write it with a y and an x. I swap over the x and the y because I'm looking for something that does this backwards, and then I rearrange it to make y the subject. So I can add 8 to both sides, I can then divide by 3. And to finish it off, the opposite of squaring a number is square rooting it. So I would have y is equal to the square root of x plus 8 divided by 3. This part here forms your working out just to see what happens when you go backwards, but the actual answer should be written in proper function notation. So the answer would be f to the power of minus 1 of x is equal to the square root of x plus 8 divided by 3. So the inverse of this function is this function. But in order to find out what this is, if it's not obvious, is you go through this process where you write it with x's and y's, you swap over the x and y, and then you rearrange it to make y the subject. And you end up with something you can then write in formal function notation. Give it a go. I've set some work on my iMaths along this line. We've also still got some vector work. Not everybody's managed to do the vector work stuff yet. So do the vector stuff first if you haven't already, and then try the function stuff. And if you get stuck, give me a shout.